Assuming that you put it where the sun is, it would stretch out to the circle of Jupiter. It's gigantic, truly unsound, and going to detonate. These blasts are among the greatest explosions of radio energy in the whole universe, creating more energy than a billion suns. Are you arranged for what is going to happen? Bug Squeeze, an enormous red, very Goliath star and one of the nearest stars to Earth, has recently gone through a noteworthy darkening that has caught attention and stirred mixed feelings all around the world. This darkening has led to hypotheses among cosmologists and the public about its potential ramifications. Some researchers believe this surprising behavior could be a precursor to a cosmic explosion, a catastrophic event that happens when a star depletes its atomic fuel and collapses under its own weight, leading to a massive blast. Such an event raises concerns not only among mainstream scientists but also among the general population, as it suggests questions about the possible impact on our own planet. Scarab Juice is a distinct star grouping, which is easily recognizable in the night sky due to its distinct shape and bright stars. Also referred to as Alpha Orionis, it holds the title of the brightest and largest star in this constellation. Recent data collected by NASA's Hubble Space Telescope, along with observations from other observatories, have shown that Creepy Crawly Juice experienced a significant mass infusion in 2019. This behavior is unusual for a star of its kind and has sparked interest among astronomers worldwide. While coronal mass ejections are a common event in our own sun, the extraordinary event seen in Scarab Juice adds an intriguing layer to our understanding of stellar life cycles and the dynamics of massive stars. The distance to Bug Juice remains a topic of debate among astronomers. Some estimates suggest it is farther away, while others indicate it could be as close as 724 light-years from Earth. Accurately determining the distances of red supergiant stars like Creepy Crawly Juice is a complicated challenge due to their enormous size and distinct properties. Creepy Crawly Juice stands out as one of the brightest stars visible in our night sky, boasting a luminosity multiple times greater than that of the sun. However, this immense brilliance comes at a tremendous cost. Creepy Crawly Juice burns through its atomic fuel at an accelerated rate, hastening the inevitable end of its stellar life. Eventually, the star will deplete its fuel supply, leading to a dramatic collapse under its own gravitational pull, possibly resulting in a cosmic explosion that could give birth to a neutron star or even a black hole. If our current astrophysical speculations prove correct, this raises an important question. Does Bug Juice pose a threat to Earth? If a cosmic explosion were to happen just a few hundred light-years away from our planet, the consequences could be devastating. The blast of a supernova can release an extraordinary amount of light, potentially equaling that of an entire galaxy. Therefore, even if Creepy Crawly Juice is relatively far away, like the star Alpha Centauri, the effects of its cosmic explosion could be significant and widespread. Remarkably, since the last cosmic explosion observed in our own galaxy in 1604, humankind has yet to witness such an event locally. However, a notable cosmic explosion did occur in 1987 in the Large Magellanic Cloud, located 169,000 light-years away. While that event had massive effects, it posed no direct danger to Earth, serving as a reminder of the scale and potential impact of such cosmic phenomena. The concept of a danger zone surrounding a typical cosmic explosion is fascinating and could have serious implications for life on Earth if a supernova were to occur nearby. Nonetheless, it's important to understand that, in the vast astronomical landscape, nearby supernovae are relatively small events compared to gamma-ray bursts, which are far more powerful and pose a different kind of threat. Gamma-ray bursts can have devastating effects, capable of destroying biospheres and saturating planets with lethal radiation. For example, a specific type of cosmic explosion can lead to the destruction of a planet's ozone layer, leaving it vulnerable to the harsh radiation of space long after the blast has occurred. This potential was highlighted in a recent study that outlined new possible risks associated with massive stars that end their lives in such a spectacular manner. When massive stars explode in a supernova, they can reach some of the brightest radiances known in the universe. In fact, the brilliance of a single supernova can surpass the combined brightness of billions of stars. This raises the question of what the ramifications would be if Bug Juice were to undergo such an explosion. If a supernova were to happen, bug juice would become the second brightest object in our sky after the sun. Remarkably, despite the distance separating it from us, bug juice, which shines brighter than a full moon, would become visible during daylight hours. The sheer force of the explosion would result in a display so stunning that shadows would be cast even in complete darkness. Such a scene would be both awe-inspiring and terrifying, illustrating the raw power of cosmic events. While the visible light emitted by a supernova is indeed stunning, it is only a fraction of the total energy produced during such an event. Although high levels of visible light can cause temporary visual impairment, the greater concern lies in the high-energy radiation emitted alongside the visible light. This radiation often manifests as X-rays and gamma rays, which can have far-reaching consequences. One of the most significant dangers posed by this high-energy radiation is its ability to catalyze the depletion of the ozone layer that protects our planet from harmful solar radiation. Without a robust ozone layer, life on Earth's surface would be exposed to extreme ultraviolet radiation from the sun, potentially leading to mass extinction events. The immediate aftermath of a supernova presents imminent risks, but over the long term, cosmic rays and subatomic particles traveling at near-light speeds begin to infiltrate the solar system. These immense rays can break down ozone layers and coat the Earth's surface with harmful radiation, compounding the dangers posed by the initial explosion. Furthermore, these cosmic rays carry a large portion of the total energy released by the supernova, and their long-term effects could linger for hundreds of years. There is evidence suggesting that such events may have affected Earth in the past. For example, elevated levels of iron-60, a radioactive isotope produced in supernovae, have been found in seafloor sediments and lunar regolith. This finding suggests that Earth may have been impacted by supernova ejecta in relatively recent geological history, perhaps within the last few million years. Astronomers have previously inferred that there are currently no nearby supernova candidates that pose an immediate threat to life on Earth based on what we know about the risks associated with gamma rays and cosmic rays. However, ongoing research has revealed new potential threats associated with specific types of gamma ray bursts. These gamma ray bursts can produce long-range lethal radiation that poses a greater risk to planets like our own. The mechanism behind this involves a star nearing the end of its life being surrounded by a significant disk of material. When the supernova occurs, a shock wave is generated, striking this disk and causing it to become incredibly hot. This in turn produces a significant amount of high-energy X-ray radiation, which can travel immense distances through space. The most radiant X-ray supernovae have the potential to deplete a planet's ozone layer by as much as half, creating conditions that could trigger an extinction event within a radius of around 150 light-years. Fortunately, no candidate X-ray supernovae have been identified in the immediate vicinity of Earth. However, this research has led to new insights regarding the cosmic habitable zone, the region within galaxies where conditions are suitable for life. These findings suggest that this habitable zone may be subject to additional constraints. Specifically, the outer regions of a galaxy may not have enough star formation activity to produce the elements necessary for the formation of rocky planets. Meanwhile, the inner regions, where stars form and die at a faster rate, pose their own risks. Frequent supernova explosions in these regions can irradiate the surrounding space, increasing the risks for any potential life that might exist there. New research shows that the inner boundary of the cosmic habitable zone may be farther from the galactic center than previously thought, reshaping our understanding of where life might actually thrive. So, what will the insect juice supernova look like from Earth? While Earth's biospheres will likely remain unaffected, the spectacle itself will be impossible to ignore. According to experts, insect juice will continue to shine brightly for more than 90 days following its explosion, reaching a luminosity equivalent to half that of the moon, several times fainter than a full moon. Essentially, it will appear as a bright point in the sky, visible even during the day. Its striking brilliance will captivate anyone who looks up, casting shadows even at night. This grand celestial event will undoubtedly be a source of fascination for people on Earth. As the supernova remains visible to the naked eye for months, its remnants will gradually fade. But researchers continue to study bug juice to uncover more about the life cycle of massive stars and the processes that lead to their violent ends. Understanding these vast phenomena is crucial for gaining insights into the evolution of our galaxy and the creation of elements during a supernova explosion. Not only is visible light emitted, but a vast range of heavy elements like gold, silver, and uranium are forged in the intense heat and pressure of the explosion. This process, known as nucleosynthesis, plays a key role in enriching the interstellar medium with the building blocks essential for future star and planet formation. Interestingly, the remnants of a supernova, known as a supernova remnant ***, can become a stellar nursery where new stars are born from the dust and gas expelled during the explosion. This cyclical process highlights the interconnectedness of cosmic events and how the death of one star can lead to the birth of others. Researchers have identified various supernova remnants that are still forming new stars long after the original explosion, demonstrating the dynamic nature of the universe. Another fascinating aspect of studying supernovae is their role as cosmic distance markers. Astronomers use type Ia supernovae, explosions of white dwarf stars that reach a consistent peak brightness, as standard candles for measuring distances in the universe. This method has significantly contributed to our understanding of cosmic expansion and the discovery of dark energy, a mysterious force driving the acceleration of the universe's growth. Moreover, the study of supernovae offers insights into the potential habitability of exoplanets. Scientists are examining how the radiation emitted during these celestial explosions might affect planets orbiting nearby stars, potentially influencing their atmospheres and the viability of life. This research underscores the importance of understanding the environmental conditions that govern life across the universe. The possibility of observing a nearby supernova raises intriguing questions about how society might respond to such cosmic events. Throughout history, supernovae have inspired myths, legends, and artistic expressions. The explosion of a star is not just a scientific phenomenon. It becomes a powerful symbol in human culture, representing change, destruction, and rebirth. In many societies, the appearance of bright new stars in the night sky has been interpreted as signs or messages from the universe. Furthermore, advances in technology have revolutionized our ability to detect and study supernovae. Space telescopes equipped with cutting-edge sensors can capture detailed images and spectra of these events, revealing their structure and behavior. Ground-based observatories also play a critical role in monitoring transient events, allowing astronomers to respond quickly to observations and collect real-time data. The future of supernova research holds exciting possibilities, as new telescopes and instruments, like the James Webb Space Telescope, are developed, promising to offer exceptional insights into the life cycles of stars and the dynamics of their catastrophic deaths. These observations could lead to breakthroughs in our understanding of stellar evolution and the fundamental processes that shape our universe. In summary, the study of bug squeeze and its impending supernova event serves as a gateway to broader discussions about cosmic development, universal recycling, and the impact of these phenomena on life and culture. The investigation of such massive stars deepens our appreciation for the intricate and often violent cycles that govern the universe, illuminating our place within this vast, ever-changing cosmos. Supernovae also play a critical role in the larger cosmic timeline, marking the end of a star's life and the subsequent formation of new celestial structures. For example, the remnants left behind can evolve into nebulae, vast clouds of gas and dust that act as fertile grounds for new star formation. These regions can harbor complex chemistry, contributing to the development of organic molecules, which are the precursors to life. Additionally, the shock waves produced by supernova explosions can trigger star formation in nearby molecular clouds. This process, known as triggered star formation, demonstrates the interconnectedness of cosmic phenomena and shows how a single sensitive event can set off the birth of new stars and planetary systems. This highlights the significance of supernovae, not just as endpoints but as catalysts for future astronomical development. In the grand scheme of the universe, supernovae also contribute to the dispersion of heavy elements throughout the cosmos, enriching the material from which future stars and planets are formed, and ultimately influencing the chemical diversity essential for life. This cosmic recycling underscores the importance of understanding supernovae in the broader context of astronomy and the origins of the elements that make up our own planet and life itself.